Hello, my name is Michael West, and today I'm going to briefly talk with you about my paper titled The Study of Complex Manipulation via Kinematic Hand Synergies, the Effects of Data Preprocessing, which was recently published at the IEEE International Consortium for Rehabilitation Robotics. So what are synergies? Synergies are the result of dimensionality reduction that extracts coordinated simultaneous movement. So for example, in the human hand, we have greater than 20 joint degrees of freedom, as shown by the graphic on the left. A synergy will suggest that rather than individually control each of these joint degrees of freedom, you may control many of them simultaneously. This is demonstrated by the middle graphic. Importantly, synergies have been used as a basis of control for both rehabilitative and prosthetic devices. This is shown in the anthropomorphic hand on the right that uses only two motorics to actuate all 20 degrees of freedom. So how do we extract these coordinated simultaneous movements known as synergies? That is through singular value decomposition. For kinematic hand synergies, you set up a data matrix where each element is a hand joint position, and the columns represent the different joints in the hand, and the rows represent time. Then, SVD decomposes this matrix into an orthonormal matrix U, which contains temporal evolutions over time. A diagonal matrix sigma, which contains the eigenvalues of the data matrix, which can be used to measure the variance accounted for by each synergy, and another orthonormal matrix V, which contains our kinematic hand synergies, otherwise known as a given posture whose joints all move simultaneously based on the temporal gain. For a random set of 2D data, as drawn here, the first synergy will point in the principal direction of motion, as shown in the blue here, and the second synergy will point orthogonal to that direction, as shown in the purple here. So now that we have an understanding of our singular value decomposition, you can imagine that different data preprocessing methods may lead to quantitatively different conclusions about these synergies. Here, we tested four. Raw data, where there is no preprocessing, mean removed, where the data is centered such that the average of each joint is 0, and z-scored, where in addition to removing the mean, we effectively squeeze the data such that it has unit variance. In range 0 to 1 data, where each joint's recorded motion is normalized such that the minimum value is 0 and the maximum value is 1. Moreover, we tested these four preprocessing methods by extracting synergies on two different types of data sets. The first was numerical simulation of a 2-degree of freedom system that allowed us to test and build our intuition. Note, specifically, the validation was guided by this equation shown here, where we have an embedded synergy of 0.5. That is, the second degree of freedom moved with half the motion of the first degree of freedom. Then, with our gained intuition, we aim to extract synergies during a complex manipulation task, namely piano playing, where we recorded the 23 joint relative positions in the hand using a device called the cyber glove of one subject playing 7 different piano pieces. Looking at our numerical validation data, what is shown here is the variance accounted for by each eigenvector or synergy. And our immediate takeaway is that when the data is not preprocessed, shown in the red here, the second synergy was considered to negligibly contribute to the variation of the data. This also occurred to a certain extent with the range 0-1 data. Here, we see the data after preprocessing for each of the different 4 preprocessing types, and the associated synergies or eigenvectors shown in red and black. One thing to immediately notice is that in this raw data case, the first synergy shown in red does not match the principal direction of the data. This is also observed in the range 0-1 data case, but isn't observable by the naked eye. Noticing this, we should look at the coefficients of the first eigenvector, which is shown here. What is important is the ratio of coefficients shown in this table below. Recall, in our equation, we have an embedded synergy of 0.5. That is, as degree of freedom 1 moves, degree of freedom 2 moves about half that. Thus, we are looking for a ratio of the eigenvector coefficients to be about 0.5. Looking more closely at this, the first thing we observe is that only the mean removed data estimated an approximately correct slope. That is, the approximately correct ratio of eigenvector 1 coefficients. So the question becomes, what is the error with the other preprocessing types? Well, to observe this, we have to look at the ratio of the mean values of the preprocessed data. That is, the average of degree of freedom 2 divided by the average of degree of freedom 1. Observing this, we see that when the data is not centered, that is, when in the raw and range 0-1 data, the first synergy was approximately directed towards the mean of the data. that is observed by the similarity in the ratio of eigenvector coefficients and the ratio of the mean values. Another thing to notice is that changing the variance of the data led to a synergy that demonstrated that the degrees of freedom do covary, but not by how much, which is why we see a ratio of eigenvector coefficients of 1 in the z-score data case. Now, with those insights from our validation data, let's take a look at the piano data. What is shown here is a variance accounted for of the first 10 synergies for each of the 4 preprocessing types averaged across piano piece. What is obvious is that these curves significantly differ depending on the data preprocessing type. Why is this important? Well, in rehabilitation and hand prosthetics, we often ignore synergies that we deem to be insignificant based off the variance accounted for curve. One such definition of significant synergies is the number of significant synergies are defined as the number of synergies required to achieve at least 90% variance accounted for, or inclusion of another subsequent synergy did not add an additional 5% variance accounted for, which is shown on the table on the bottom left. A key takeaway is that there is a significant effect of preprocessing type on the number of significant synergies, which can greatly affect the number of synergies you incorporate in your prosthetic or rehabilitative device. Moreover, we see here that trends in the variance accounted for of the first eigenvector are similar to those seen in the numerical validation data, where we see that dominant first synergy in the raw data and the range 0-1 data, shown on the graph in red and gray. Okay, so before we look at the actual synergies of the piano data, let me introduce cosine similarity. Cosine similarity is a measure of the angle between two vectors. The cosine of 0 is 1, indicating the two vectors are the same, and the cosine of 90 is 0, which indicates the two vectors are orthogonal. Cosine similarity comparison can be generalized to a matrix of vectors. In our case, a synergy matrix is just that, a matrix of vectors, V. If we take the matrix multiplication of the transpose of a synergy matrix times another synergy matrix, then we get a matrix of cosine similarities. And if these two synergy matrices are the same, this will result in a cosine similarity matrix that is the identity matrix, which has 1s on the diagonal and 0s everywhere else. With that in mind, shown here, we see 6 cosine similarity matrices of the 6 comparisons from our 4 preprocessing types. What we notice is that our cosine similarity matrix is not the identity, which has values of 1 on the diagonal, shown here in black, and 0s everywhere else, shown here in white. What's interesting is that high similarity is seen on the subdiagonal upon comparing the synergies from the raw data and the mean removed data. Additionally, high similarity is seen on the superdiagonal upon comparing the synergies from the z-squared data and the range 0-1 data. Why does this occur? Well, insight can be drawn from our numerical validation data. Recall from the numerical validation data, when the data was not centered, the second synergy was considered to negligibly contribute to the variation of the data. This is shown on the graph on the left in red and gray and in the table highlighted below. Additionally, recall that when the data was not centered, the first synergy was approximately directed towards the mean of the data. This was shown by the similarity of the ratio of the mean values in the data and the ratio of the first eigenvector coefficients, highlighted in the two tables here. So, with those insights in mind, the high similarity in the off diagonal suggests that not centering the data will lead to a dominant first synergy with subsequent synergies that are consistent with the synergies of the centered data. So what have we learned from this? Well, we looked at the effect of 4 preprocessing types on the extraction of kinematic hand synergies, and we learned that 1, not centering the data leads to a dominant first synergy that is not representative of the principal directions of motion, and this will lead a researcher to ignore the also important lower order synergies. And 2, changing the variance of the data will lead to a synergy that demonstrates that certain degrees of freedom do indeed covary, but will not quantify by how much. Thus, we recommend the preprocessing step of removing the mean. The understanding of how preprocessing affects synergy decomposition presented here can better inform the selection of and the quantity of the kinematic coupling of synergies that assistive and prosthetic hand devices should implement. Lastly, I want to thank my co-authors, Drs. Federico Tassari and Professor Neville Hogan, and my funding sources. And I want to thank you guys for making it to the end of this video. If you're curious to read the paper, I'll put the link in the description below. And as always, don't hesitate to reach out if you have any questions.